Okay, guys, for this part of the lesson, we are not going to be given a graph. Instead, we're either going to be given an equation or a function table. So here is the test, and we kind of have already been talking about it, and it looks a little complicated maybe, but it really is not. So all we're going to be doing is replacing any x value in our equation with negative x, and then simplifying. If we get out the exact same equation, then it is even. If we get out the exact opposite, then it is odd. And if neither of these things happen, our function is described as neither. So all this is saying is that the output of our negative x and the output of our positive x are the same. That's what this notation means. So let's take a look at example 1. Let's just take a look when we have no actual input values. I'm going to replace my x with negative x as we have here. So I'm going this way, guys. So let's expand negative x squared. And now let's simplify. A negative times a negative is positive, and I end up with the exact same equation. This means I have the exact same outputs. When I put in negative x, I get x squared minus 4, and when I had a positive x, I got x squared minus 4. Now let's look at an actual value. So this time, when we put in 3, we have 3 squared, which is 9, and then minus 4 gives us 5. Now let's look to see what happens when we put in negative 3. Negative 3 times negative 3 is 9 minus 4. And indeed, we do get out the same output. It's all about the output. When we put in an x and its opposite, if we get the same, it is even. And that's what this notation right here means. When I put in x or its opposite, I have the exact same output. And this shows us in a graph, in the equation, and in a function table. So you can see that, let's change our color so we can see this. If we have positive 2 and negative 2, I have the same outcome. So when I put in negative 2, I get out 0. And when I put in positive 2, I get out 0. We have the same outcome. We have negative 1, I get out negative 3. And when I put in positive 1, I get out negative 3. So that's what makes it symmetrical about the y-axis. If we were to plug these points into our equation, we would see that we would get the same output. So when I put in negative 1, I get out the negative 3. When I put in positive 1, I get out the 3, the negative 3. So you can see my outputs are the same. Now, let's look to see what it means to be odd. It means to be odd is if the outcomes are opposite. So let's take a look at this example. We have a cubic function. So when I put in a positive x, this is the outcome I get. We want it to be what's called negated. We want the opposite of this. So let's see if that happens. When I put in a negative x into my function, and let's expand that, a negative times a negative is positive times a negative is negative. So whenever I put in the opposite, here's my outcome for when I put in the opposite negative x. When I put in negative x, I get out negative x cubed. When I put in positive x, I get x cubed. These are opposites, therefore it's odd. So let's take a look at an actual value. When I put in 2 into this function, when I have positive 2, I get 2 times 2 times 2, which is 8. And when I put in negative 2, I want the negation of 8. And so I have negative 2 times negative 2 times negative 2. This gives me 4 times negative 2, which gives me the negative 8, the negation. So these are symmetrical about the origin. So again, if I have 2, comma, say that's 8, and then we have negative 2, comma, negative 8. These are symmetric about the origin. So here is the notation for this. When I have x and then its opposite, my outputs have to be the opposite. Here is an example of a graph, the equation, and the function table. So we can see that on this table, when I put in negative 2 and positive 2, the outcomes are opposite. When I put in negative 1 and then positive 1, the outcomes are opposite. This makes it odd. Most functions are neither odd nor even. So when we're doing this test and we don't get the exact same outcome or the exact opposite outcome, we describe them as neither. So let's take a look. Here we have an even exponent. So we're just going to ask, is this even? Just because it has an even exponent doesn't mean it's even. So we have to test it out. So we're going to plug in negative x. We have negative x times negative x minus 2. And again, to be even, we want the exact same outcome. A negative times a negative is positive minus 2. We do indeed have the exact same outcomes. So this is called even. And if you wanted, we could plug in some ordered pairs and test it. So let's plug in when x is, let's do 3. And then we'll look to see what it looks like when x is negative 3. So we have 3 squared minus 2, that's 9 minus 2, which gives us 7. Remember, we're wanting to be symmetrical about the y-axis. Now let's put in negative 3. And we get out the same outcome. So these are reflecting across the y-axis. They are symmetrical. Okay, here we have a cubic. Let's see if this is odd. What we're looking for is the negation. The negation would be negative x to the third plus 2. That's what we want to be odd. So let's see. Are we going to get this outcome? We're going to plug in negative x. We're going to expand. A negative times a negative times a negative is negative minus 2. So we got the negation of the cubic term, but not our constant. So this is neither. We're looking for the same or the exact opposite. To be opposite means to be negated. Every term needs to have the opposite sign as the original. Okay, here we have an exponent of 1. Let's see if this is odd. The negation would simply be 2x. So we're going to plug in negative x everywhere we see an x. Negative times negative is positive, and we do indeed get the negation. So this is odd. Here, let's see if this is odd. So we would want the negation would be negative 3x plus 1. That's what we're looking for. We're going to plug in negative x. Positive times negative is negative. So we do not have the total negation. We have the negative 3x, but this needed to be plus 1. So this is neither. It does not go through the origin. You could even test that. If I plug in 0, I would want to get back 0. So if I put in 0, I'm looking at my original equation. So oops, 0 minus 1. So when I put in 0, I get -1. It doesn't pass through the origin. Okay, now this is a quadratic, so we're going to see if it's even, and we want the exact same outcome. And here I have a negative and a negative, so I'm going to simplify by bringing that negative out, and I have x plus 1, and I do not have the same, so this is neither. And we could plug in a couple points if we wanted to test this. Here, we're going to see if this is odd. What are we looking for? The negation would be negative x cubed minus 1. This is what we would want. This is what we're looking for, guys. We get the negative x cubed, but we get plus 1 and not minus 1. So this is neither. And we can see it does not go through the origin. If I plug in 0, I get out 1. Okay, let's take a quick look at some function tables. And we pretty much have been talking about all this. You can pause the video and write these down if you would like. So to be even, it does not have to go, have to pass through the origin, but each input and its opposite must produce the same output. So if we have -2 and +2, they should have the same outputs. And we can see here that these are examples. The odd function, they must pass through the origin. So that's one quick test you could do to see if it is odd. And each x value and its opposite must produce the opposite outputs, just as you see here. When I have 1 and -1, they give me opposite outputs. Just as on the second table, when I have 1 and -1, I have opposite outputs. Okay, so even, odd, or neither, it does pass through the origin, so that would be important to say if it's odd. Now let's take a look at -2 and +2. I get out opposite outcomes. The same with 1 and -1, these are opposite of each other. So this is odd. And again, you could plot these points on a graph to see if it's symmetrical about the origin. Here we have -2 and +2. I get the same outcome. On my -1 and 1, I get the same. So this is even. It will be symmetric about the y-axis. Okay, here we have -2 and +2. I get the same outcome. We have -1 and 1. I get the same outcome. This is even. I have -2 and +2. I get the same. -1 and 1, I get the same output. So this is even. Here I have a -2 and a 2. I get out -4 and 0. They're neither the same nor opposite. So this is neither. And I hope this helps. Remember, it's all about being symmetric about the y-axis to be even or symmetric about the origin to be odd. If it's neither one of those, then we describe our function as being neither.